Okay, thanks everyone for being here. It's my pleasure to introduce Olivier Guyon. Olivier is a professor and astronomer at the University of Arizona and a project lead at the National Observatory of Japan. He received his bachelor's degree at ENS Paris in 2000 and his PhD from Pierre and Marie Curie University, also in Paris. He's most well known for his work in high contrast imaging and planet detection, which is in many ways foundational, ranging from theoretical analysis to practical implementation. Just a short list of accomplishments include a deep analysis of the fundamental limits to exoplanet imaging, the invention of the IfA coronagraph that will be a strong contender for what's now called the Habitable Worlds Observatory, formerly IRUV, launching in the 2040s. A method of detecting planets astrometrically with small dots on the primary, and a citizen science project using small robotic telescopes to discover transiting planets. Actually, he's on a meeting about that one during this colloquium. Speaking personally, his papers are unusually deep and full of ideas, and you can take a single paragraph from them and build interesting multi-year research efforts to explore these ideas fully. Olivier is also an avid amateur astronomer and has built several unique telescopes for naked eye observations. And for his wide-ranging contributions, Olivier was awarded the Presidential Early Career Award for Scientists and Engineers, as well as more recently the MacArthur Fellowship. So with that, take it away, Olivier.
Thank you, Mike. Thank you for inviting me to talk about my favorite topic, imaging exoplanets, and I'll especially try to focus on the path forward to image habitable exoplanets, planets that orbit other stars at the distance from the star such that are potentially habitable. They can host life as we know it. So it's been a lot of fun lately to watch the amazing discoveries in exoplanets. Here are a few examples. I chose to highlight these examples because they are very related to the technical aspect of the talk today. It turns out most nearby stars have habitable planets. Actually, maybe not most, but a significant fraction, and they're around M-type stars. So the nearest star to us, for example, Proxima Centauri, has at least one habitable planet, maybe 1.5. And another, and sometimes planets come in large number. The TRAPPIST-1 system, which is a little bit more distant, has several planets that are in habitable zone, probably rocky planets. So there's no longer a question of do such things exist, potentially habitable planets, essentially rocky planet in habitable zone. They do exist. We start to have statistics about them, but we really don't know much about what is going on in their atmospheres and if there's actually life emerging on these planets. And that's really the next big step in this field, and that's the one I'm going to be talking about. So why should we image habitable planets? Why should we image planets at all? If you're trying to discover planets, direct imaging is about the hardest thing you can do. Planet is very faint compared to the star. It's sitting right next to the star. It's much easier to detect a planet by looking at perturbations on the starlight itself, whether it's transit, the planet passes in front of a star, or it's a gravitational perturbation detected by spectroscopy with radio velocity or astrometry. Direct imaging is hard, but the motivation for direct imaging is to get high quality spectra of the planets to study their atmosphere. And here's an example of a spectra of a definitely habitable planet. It's Earth. And this spectra was taken not by flying a satellite looking back at Earth, but actually looking at the moon. If you look at the thin crescent of the moon, the Earth shine is actually light from Earth shining on the moon, and so you can take a spectra of it and get a spectra. And if you divide it by the spectra of sunlight, the sunlit part of the moon, you get a reflectance spectra of the Earth, and that's what was done in this example. And the interesting thing, there's lots of interesting things. You can see there's Rayleigh scattering, excess of light in the blue, confirmation that our planet has an atmosphere. There's a very strong oxygen line. There are water lines that get progressively stronger as you move to the near infrared. And there's even this jump, this vegetation jump. So plants are quite reflective in the very near infrared, and we can see that in the spectra of Earth. So the goal is to take spectra like this, but not for Earth, for other planets. So why is it hard? I think this picture really illustrates the challenge of the problem. This was a picture taken by the Cassini spacecraft before it plunged into the atmosphere of Saturn. So this particular picture was taken when the spacecraft was in the shadow of Saturn, looking back towards the inner solar system. The rings are beautiful. There's lots of things that are interesting in this picture that are related to Saturn, but I want to draw your attention to this little dot. That's us. Earth plus Moon is this little dot. So as soon as we leave the vicinity of the inner solar system and look back, the Sun is about 1 billion to 10 billion times brighter than Earth, and the Earth is right next to the Sun. So this is a very challenging problem, a high contrast imaging problem, where we have the combination of a large ratio between the flux of a star and the planet, and also close proximity, angular proximity. And if we zoom in, so this is us. All of us are on that picture, on that pixel here. So what do we need to do to solve this problem? So we need large telescopes. The largest telescopes are the ones on the ground, but unfortunately, they're sitting in Earth's atmosphere. So the first challenge is atmospheric turbulence. If we take an image of a star, so this is a simulation. If we take an image of a star, a nearby star, with a large ground-based telescope, this is what we see on the lower left here, a big blob of light. This is about an arc-second across. That's what we call the seeing size, the angular blurring size imprinted by the atmosphere. So the first thing we need to do is correct for this aberration, this wavefront errors that are imprinted by atmospheric turbulence. If we do a really good job at it, we get the image in the middle. So now the starlight flux is concentrated, and instead of being limited by this incoherent halo of essentially atmospheric blurring, we become limited by the diffraction of the telescope itself, which is fundamentally due to the wave-like nature of light. But the good thing is we know exactly what that is. We can compute it in a computer very accurately because we know the optical prescription of the telescope. So we can design optical masks to take that out because it's a static effect we can compute. We know exactly what it is. And that's called a coronagraph. And if we deploy this optical mask, we get the image on the right, where through the adaptive optics correction of the turbulence plus the cancellation of diffraction with a coronagraph, we get a high contrast image where we can look for planets. Now, it's most likely the planet is still quite a bit fainter than the residual light because the adaptive optics is not perfect. There's some residual, but we can be in a situation where we've attenuated starlight by a factor 10 to the 4, 10 to the 5, and we can look for planets that are maybe 100 times fainter by doing careful image analysis. So we have a program at the Subaru Telescope that develops such techniques. So this is a picture of the Subaru Telescope on top of Mauna Kea. And if we go inside the telescope, so this is looking down into the telescope, and on the side, on the NASMIS focus, there is this instrument, the Subaru Chronographic Extreme Adaptive Optics System, which is where we're developing these technologies. And we actually do two things at the same time. We're open use instruments, so astronomers can use it to do their science, but we're constantly upgrading it and developing it in collaboration with multiple groups to basically help drive this technology forward. So we're ready for when bigger telescopes, 30-meter class telescopes, are deployed to go after habitable planets. So this is a picture of the instrument. We're fortunate at the Subaru Telescope, there's a large NASMIS platform, so we can work on the instrument as if we're in a lab. The telescope is not even visible from here, it's behind that wall. And this is us observing at night. So we're just looking at computers, essentially. The striking thing in an extreme adaptive optics, a sort of high contrast imaging instrument, is everything can be very small, and it fundamentally is due to the fact that we don't care about field of view. We're looking for planets that are essentially within 1 arc-second of a star, so we can make everything small. We don't need to maintain large angles, and we can shrink the pupil. So that we definitely took advantage of this at Skexeo. We made everything very small and packed a huge amount of hardware to test all sorts of modes. I'll point out a few things. So we have, I am getting lost here. So you notice some of the mirrors are gold coated. That's because much of the science is done in the near infrared. But there's a whole arm of the instrument that's working in the visible. You can see multiple cameras, filter wheels. There's a lot of optical masks involved. There's even single mode fibers. I'll talk a little bit about that later on. And so let's go to the next slide. So again, the goal of the instrument is, first step, we do a really good job at adaptive optics correction. So we get the image in the middle. Then we deploy a chronograph to cancel starlight. We get an image like this. So now I'll switch to actually real images on sky. This is a real image on sky. The star is blocked. Those 4 spots are calibration spots we add because we've blocked the star. We still need to know how bright it is and where it is. So we add this spot. You can see we're limited by diffraction. And so we have, this is basically a regime where the image is becoming quite stable and we can look for planets. And then with some image processing, we can recover planets as shown in this lower right image. One of the critical elements of all of this is a wavefront sensor. It's the device that looks at the wavefront, at the starlight, to figure out what exactly are the optical aberrations that need to be corrected. Our main wavefront sensor is a pyramid wavefront sensor. Without going into too much detail, light from the telescope is focused in a diffraction spot. There is a glass transmissive pyramid that's located at that spot. It splits the beam into 4 copies. And the distribution of light between the 4 copies is telling us essentially what are the wavefront errors that are coming in. So here are some examples of what happens with different scenario of in a simplified case where we have a perfect airy disk with 2 side speckles. So this is real images on sky. So I snapped those. They're perfectly synchronized. On the right is this wavefront sensor image, which encodes what are the aberrations in the system. This is while the loop is the adaptive optics loop is running. On the left is a visible light image. This is double star separation of 0.3 arcseconds, and in the middle is near infrared. There are actually 2 copies because we're doing polarimetry at that point. The key here is you can see that when we turn off the adaptive optics system, we're operating at the diffraction limit, even in a visible. Especially in this image, if we turn off the adaptive optics system, this star becomes a very big blurry mess that would extend to the whole field of view of this image. Some more examples. This is a video image in the near infrared, so you can see when the adaptive optics loop is closed, it's very stable. We're limited by diffraction. The strial ratio is quite high. We can run the system up to 3.5 kilohertz speed, the deformed mirror, as we correct typically a little more than 1,000 modes, 1,200 modes. This is in the visible, 750 nanometer, nice diffraction limited PSF. So we routinely achieve the diffraction limit in the visible. Here's an example of a double star. You may not realize Capella, one of the brightest stars in the sky, is a double star. The separation is 46 milliarcseconds, and they're very well separated. So I'll show a few examples of the type of science measurements we take with the current instrument, and then the second half of the talk, I'll talk about development, things that we're working on for future capabilities, especially related to habitable planets. So I showed you an image of Capella, a double star. This is a measurement that was taken with one of the modules of the instrument, which is actually a little interferometers using single mode fibers, measuring the orbital motion of Capella. And it's hard to see the error bars. You really have to zoom in. Capella is a double star. The period is about 100 days. And if you look at the error bars, the vertical error bars here, this is 2 measurements we took 1 day apart. So you can essentially see the orbital motion almost in real time. Within an hour, we can see the orbital motion of this double star. Sébastien Vievard led this work, and there's a paper under review. Another spectacular measurement, which was taken by Miles Luca, who's actually in the audience, University of Hawaii's PhD student, is a disk around a star. So we do a lot of research on planet formation, and imaging disks is very important. So I'm showing this because this is a disk that's quite massive, and this was imaged in the visible, where we achieved the diffraction limit. This is an image in intensity, and this is an image in polarized intensity. And the advantage, so this disk had previously been imaged in the near infrared. This is an image from GPI, but in the near infrared, the diffraction limit is not as good, so it's a little more fuzzy. By going in the visible, we get a lot more details. We get a very fine structure. There is, for example, interest in what is creating this gap. So I'm sure that there's going to be a lot of discussion about what all that structure really means, but you can see it's much sharper than if we were doing this in the sorry, I need to mute my phone. A lot sharper than if we were in the infrared, and also going much closer into the inner part of the disk, which is really important because it's related to habitable zones. We want to be able to map planet formation, planet evolution, and image planets in the habitable zones, not at the distance of Jupiter or further out. I mean, we also want to do that, but we're very interested in going very close in. Another recent discovery is we discovered a protoplanet around the star AB Auriga. So this is a montage where the red is from ALMA. ALMA had identified a big disk, a ring, and we found a thermal emission source just inside this ring. This is a more detailed image, and this discovery was quite important because it's really strong evidence that planets can form from gravitational collapse of gas in massive disks, which is a little bit different from quite different from the main formation mechanism that is thought to be prevalent for planets, which is core accretion, where you start with rocky pebbles that essentially grow slowly. This is a much quicker formation process where gravitational collapse basically takes over and quickly forms a planet. And one of the things that was quite important in this discovery is having multiple measurements. So I showed the ALMA disk, which was indicative there was a very nice ring. So it's indicative that there may be a body, a massive body inside that ring. And with the SCEXO instrument, we took measurement in thermal light, where we see the protoplanet, in polarized intensity in the near infrared, where we don't see anything, which is good, because if this was a disk structure, it would actually show up in polarized light. It would scatter starlight. And we also see it in the visible in emission, in hydrogen alpha emission, which is indicative of ongoing accretion on the protoplanet. Another recent discovery, this is going to appear in Science, is the first confirmed planet discovered by Gaia. So it used to be that we were randomly hunting for planets around bright stars with no a priori data on the existence of such planets. Gaia is a space astrometry mission operated by ESA, and it measures the position of stars on the sky very accurately. So if there's a planet, a massive planet going around the star, we see the star wobbling essentially. And now we're using data from Gaia to actually pre-select stars that shows this acceleration, and this is turning out to be very successful in discovering planets. So this is this is actually the first time that Gaia was used to discover a planet, which we were able to confirm. We constrain the mass, so it's a sort of the planet upper mass boundary at 16 Jupiter mass. The orbit is well constrained, and we get a spectra. And we also have actually another second discovery of a planet using the same technique. So this is fresh and will come out at some point in a referred paper. But I'm going to spend the rest of my time talking about the future, and the future is larger telescopes. Everything we do right now is planet formation, massive planet imaging and spectroscopy, but we're not able to image habitable planets yet. And for that, we need bigger aperture. We need more sensitivity, and we need better angular resolution. So there are three telescopes projects, three extremely large telescope projects that are basically being built right now. 30-meter telescope. I don't think I need to tell you about it, especially I don't need to tell you how big it is. It's in the name, but it's really big. The Giant Magellan Telescope, 25-meter. So when I was a student, a grad student, I was amazed at the 8-meter, 10-meter class telescope. drawings because they would put a person next to it, and the telescope was much bigger than the person. So this is a person here. It's really hard to see. So now the new norm is to put a truck. So this is the truck next to the telescope, and this is the European Large Telescope, 39 meter with the mandatory dump truck here. And I don't know if there's a person in that picture. It would be actually hard to tell. So there are teams, international teams, working on designing designing instruments to image exoplanets on these telescopes. Here's an example of one such conceptual design. This is called the Planetary System Imager. This is for the the 30-meter telescope. And these have all the ingredients I told you about: extreme adaptive optics, advanced wavefront sensing. There is a lot of spectroscopy because we want to characterize the planets, and the instruments work in essentially near infrared and visible, with possible extensions down to the thermal infrared. So it might be surprising to think that we can image habitable planets with telescopes on the ground, because if you're used to sort of the canonical Earth Sun system, the contrast is 10 to the 10 or 10 to the 9, which is really hard to get from the ground, even if you do a very good job with adaptive optics. But there's actually a sort of complementarity, a trade-off, depending on the star you choose, between the contrast and the angular separation. So here is a drawing where I took all stars within 30 parsecs, there's about 6,000 of them, and I magically plopped an Earth-like planet around each one of them, and at the right distance, so the temperature is the same as Earth. And I show them here in two axes. This is the contrast in log 10. So this is 10 billion, this is 1 billion, this is 1 million up here. So up here is easy, down here is hard / impossible. And the other axis is the angular separation. So one arcsagon is here, 1/10 of an arcsagon. This is 10 milliarcsagons, again in log scale. So this corner is the impossible corner. This corner is the easy corner, where of course there's no such planet. But you can see there's a trade-off. You can if you're in space, you can get to very deep contrast, 10 to the 10 or 10 to the 9. But your telescope is not going to be as large, so you're going to target these planets. They are the planets around sun-like stars. But if you're on the ground, where you have access to much larger telescopes, but definitely not as deep a contrast, you're going to target these stars, and those are the cooler M-type stars. What is happening is a cool star has its habitable zone closer to the star because the star is fainter. So to get the same amount of flux, about a kilowatt per square meter on the surface of a planet, you need to have the planet sit pretty close to the star. But because the star is fainter, the contrast between the planet and the star is much more favorable. So we're talking about, so this is actually Proxima Centauri. So we're talking about a contrast somewhere around 10 million to 1, which is hard, but possible from the ground, and an angular separation of for this target is about 37 milliarcsagons at maximum elongation, which is well within the diffraction limit of a 30-meter class telescope. So those are the prime targets for large ground-based telescopes, and it's really a trade-off. When we talk about let's talk about wavelength. What is the optimal wavelength coverage? There's two ways to look at it. We can look at spectra and of modeled planets, and it tells us that so this is the visible and this is the near infrared. Shows that really we want as wide a spectral range as possible, but there's a lot of value in the near infrared. There's easy detections of deep molecular lines, absorption bands, especially water, oxygen, CO2, and so this is a prime real estate in terms of wavelength. And if we think about the trade-off then in wavelength, going blue is hard because the wavefront control is hard. It's hard to maintain the contrast at short wavelength, just because the wavelength is shorter. Going red, going to the near infrared, is hard because the diffraction limit of the telescope is getting bigger. So we lose more and more of the planets because they get within essentially the diffraction limit of the telescope. If we do a little bit more detailed modeling and we look at how many planets, when I say planets, it's really how many stars could we, around how many stars could we detect a habitable planet if it existed, we see the near infrared is actually the best. And it's sort of between I band and K band that these numbers peak. And if we look at this diagram in detail, we can see that as we go to redder, to longer wavelengths, we can get deeper contrast, but we lose the inner planets because we don't have the diffraction limit. The diffraction limit gets too big. But if we go to the blue, we have plenty of potential targets. They're the open dots, open circles, but the ones that are filled, the ones for which we have the contrast, there's fewer of them because we lose contrast. So we're squeezed between contrast and diffraction limit. That's okay because, as I mentioned, the near infrared is actually the really prime real estate for characterizing this planet. So this is, again, going back to this graph, this box is where we want to work. Those are the prime targets. And depending where we put our cutoffs in angular separation and contrast, there's a few dozens of them, of stars that are around which we could potentially detect directly image habitable planets. But if we take one of our high performance adaptive optic system with a coronagraph as operating today, and we just put it on a large telescope, we don't quite get into that regime. So this is an approximate sort of detection limit. There's a lot of scaling hypotheses that go into this. So this is, don't read too much into it. This is quite approximate. But basically, we need the technology developments to get into this regime. And we need two things. We need coronagraphs to work closer in. We need them to work at 1 to 2 lambda over d, so right next to the diffraction limit of the telescope. Most of the coronagraphs we have tend to work at 3 plus. So we're really not doing a good job at this angular separation. And we also need to push the contrast deeper, especially closer in. So I'll finish by talking about, there are many areas of technology development that are moving us in that direction, but I'm highlighting 3 of them, which are particularly transformative and for which we see a lot of recent development to which we're participating. Advances in wavefront sensing and control is key to enable deeper contrast, essentially removing as much of the starlight as possible where we look for planets. Self-calibration is another area where we, by being smarter about the way we process the image, we can remove what we call the speckle noise, the sort of uncalibrated leftover starlight, and work at the photon noise limit. So this is another area that's quite promising. And I'll talk about photonic nulling, which is a completely different way to approach the optical challenge, and it's key to get much closer to the star. IWA stands for inner working angle. That's how close we can detect planets from stars. So the first thing, advances in wavefront sensing and control. I'm breaking it down in 4 branches: more sensitive wavefront sensor, smarter algorithms, integration between the adaptive optics and the image itself, and interferometric wavefront sensing. So very quickly, we are actually still finding out better ways to do wavefront sensing. This is one example. This is called the nonlinear curvature wavefront sensor. These are simulations that show that it works better than in simulation than the solutions we currently have. And this is actually a demonstration in the lab. This was done by Kyuhun An. And you can see this is actually lab images, and this is the actual wavefront sensor input. So 4 different images of the pupil at different conjugation. This is the input perturbation, the estimation, and the residual. This was done in the lab, actually just up the road. So you can ask Kyuhun to give you a tour of the lab if you're curious about this. But this is something that actually the Kyuhun is already demonstrating in the lab, and we're going to be installing it on the telescope within a year. There's a lot of development into algorithms. And it used to be that when we talk about an adaptive optics control system, we were thinking of a very simple sort of block diagram. You have a wavefront sensor measurement, a control matrix, you multiply the 2 and apply an update to your deformable mirror. Things are getting much more advanced and interesting. We're increasingly doing predictive control, being smarter about using past measurements as well as the most recent one, and sensor fusion, being able to ingest multiple measurements from multiple wavefront sensors that each have their own strengths and weaknesses. So example of on-sky demonstration of predictive control. This is without and with predictive control, and the rest, the control matrix becomes these data cubes with a time dimension. So they grow in size. Instead of being one matrix, they become essentially a series of matrix. And so this was on-sky demonstration of predictive control. It's factor 2.5 gain. This is not as much as we hope, but it is very helpful. And the image is also more stable. This is a on-off comparison of the variance, not the flux itself. Increasingly, we're ingesting, we're taking the focal plane image itself, where the speckles appear, as an input to wavefront sensing and control. This is lab work done by Kyuhun again, and showing that we have the algorithms to carve a very dark area in the image. And that's really important to be able to do that, because this is the location where speckles manifest themselves. This is where we want to work. This is the best location to detect speckles, because that's where they appear. And so gradually we're including the focal plane as part of the adaptive optics loop. And this is also becoming possible with advances in detector technologies. Now we have detectors that have very low noise at high frame rate, so we can do this type of work. Another example by a PhD student, Noorskaf, who's actually defending in a little more than a month. And this is basically watching the focal plane image so that we tell the adaptive optics system to learn what it should be doing. And so and this is a sequence of image where the adaptive optics system tunes itself by looking at the focal plane image. And finally, there is a new family of wavefront sensing approaches which uses interference, which are highly sensitive. This is work done by Sébastien Vieva and Vincent Deo, where this is an interferogram on actually Capella, where there is a very sensitive encoding of the wavefront error. So the second area of development I wanted to mention is self-calibrating for high contrast imaging. So right now, if you observe using an adaptive optics system, you have bad wavefronts coming in, they get fixed by the adaptive optics loop. The adaptive optics loop, the way it works is it's got a wavefront sensor which tells it those are the aberrations that happen, this is what you need to fix. And then we integrate a science image which still has a lot of speckles, and we give that to the astronomers and tell the astronomer, good luck, there's plenty of speckles in your image, there may be a planet. What we're trying to achieve is taking, we realize that the wavefront sensor tells us every millisecond what are those speckles, where are they? It's encoding the wavefront errors. What we're gearing towards is not throwing away this, but storing it, computing from each wavefront sensor frame what is the location of the speckles, integrating it so we have a reconstructed image of the science detector, but with just the starlight, with just the speckles, and then we can subtract the two and give to the astronomer, give to the happy astronomer a calibrated image where there's no speckles. So that's the goal. The hard part is this arrow, how to go from wavefront sensor to PSF, and there's a lot of promising work that's being done in that, but that is quite a transformative change, because now we can be limited by photon noise instead of speckle noise. So we're talking about potentially orders of magnitude gain. And one question that I often get is, well, if you have data about the wavefront aberrations, why don't you just use it better to do a correction, and then you don't need to do all this complicated thing? There's a fundamental reason why we want to do that. It has to do with latency. So when we operate an adaptive optics loop, we get a wavefront sensor frame that actually is already too old because there's latency in the system. So we don't see the wavefront as it is right now. We see it as it was a couple of frames ago. And this gets even worse when we take into account that the star is not infinitely bright. So we have to average past measurement. We're trying to overcome this with predictive control. So we take the old measurements and we predict what it is actually right now based on the old measurements, but there's still a lag. If we do this in post-processing, not only we have access to the wavefront at the exact time of the exposure, but we have access to the past and the future because we're doing this in post-processing. So it's much more powerful in estimating what is the state of the speckles essentially at the time we need it. And there's some very encouraging work being done using neural network. This is a wavefront sensor image. This is the prediction, and this is the real image. And there's a very good match between the two. I'll skip this for time. And the last technology I want to highlight is photonic nulling. So the way we do optical starlight suppression right now with coronagraphs is we design masks that we put in the image, and then sometimes we also put masks in the pupil plane. But we're very constrained when we do that in what Fourier optics allows us to do. A much more powerful approach would be to be able to freely do whatever coherent interference we want to do from whatever parts of the beam to optimize this process of suppressing starlight. And there's a very elegant way to do this, which is enabled by photonics technologies. So you can take the beam of the telescope, you can couple it in waveguides, single mode fibers essentially. Then you can enter a photonic chip, it's the equivalent of an electronic chip, but with light, where you can design the chip to do exactly what you want. You can design it to cancel light in ways that are not possible with Fourier optics, with masks. And then at the output, you have spots of light that come out, and you can disperse them to get a spectra of each one of them. So what you want to design this to do is have some of the spots be as dark as possible. They're the ones where starlight will get canceled, but if there's a planet, it'll show up. And some of the spots, the ones that have the starlight, you want to use them for wavefront sensing. They encode the optical aberrations very accurately. So you could design a chip to do everything that I've been talking about, essentially the wavefront sensing and control, and the starlight suppression at the same time. And you get spectroscopy at the end. So it's a very elegant and especially compact solution. Compact means it's going to be very stable also, which has a lot of benefits. So we have a program where we're testing this technology. It's called Glint. It's a module of SCEC. So it came in a little bit later than the other modules, so we didn't have room to put it. So we slapped it on the side here. So this is that box. It's shown here. And this is actual data on sky from this instrument. Each line is a spectra. And you can see the ones that have the green arrows are the ones where there's starlight, and the ones that are the red arrows, they're called N something, null. They're the ones where the chip is designed to cancel starlight, and there's very little light in those. So this is already starting to work on sky. I'm going to finish by showing you that we can combine all of those things together. One of the very powerful things with this technology is it should be very good at self-calibrating itself. At the output of the chip, we get at the same time the science data, and we get the wavefront sensor data. So we looked at, can we use the wavefront sensor data to calibrate the starlight data? And this was done on a bright star because the camera we used was not very sensitive. But on the left is uncalibrated, on the right is calibrated. The red box is what matters. This is the null output. This is where there's signal. And you can see that it's, this is the flux, and this is the variance, the standard deviation, and you can see the flux in the calibrated is much deeper, and the standard deviation has almost reached the fundamental noise. I'll just mention to finish that the Subaru Telescope has, I mentioned this SCEC instrument where we're developing a lot of these technologies, and we have many active collaborations to develop them. And I'll just show my conclusion slide. I think one thing I didn't mention, but hopefully is quite obvious, is that there's a lot of new technologies around the corner that should yield major gains in our ability to detect, image, and characterize planets. One of the challenges is we can't show up at one of the ELTs, at the TMT or GMT or ELT, with something that hasn't been tested and put it on sky. So what we're doing is essentially building up a program where we test things on current telescopes. And it's not just testing the hardware, it's also training the people, the young student that will basically live long enough, have a long enough career to reap the benefits of all this. And so that's really what this is all about. And I have funding acknowledgements. We enjoy support from multiple organizations through our collaborations. Thank you very much.
Okay, why don't we start with this room? Any questions from anyone? Miles?
Can you talk a little bit more about the trade-off between spectral resolution and like signal to noise, wavefront control, and some of those considerations when thinking about the next generation of spectrographs?
Can you repeat the question? Yes. So the question that Miles is asking is, what is the trade-off in terms of spectral resolution and signal to noise? So what is the optimal spectral resolution for maximizing signal to noise and also wavefront sensing? There's two possible ways to look at this. One way, which is the traditional way, the usual way, is we decouple the spectral resolution for science versus basically the adaptive optics and calibration loop. In that case, we have a lot more freedom, and that pushes us to high spectral resolution because it's better for characterizing planets. And then it very much becomes bounded by the performance of the detector. There is no cost fundamentally in getting very high spectral resolution if you have noiseless pixels and lots of them, and you have enough money to pay for them. There is sort of three regimes. There is the low spectral resolution where you just get colors, so it's essentially a more efficient way of doing sort of filtered imaging. There's the intermediate spectral resolution where you can see the broad absorption bands, and then there's which is at maybe somewhere around 100, and then there's the high spectral resolution where you can resolve fine lines within these bands at resolution of 10,000 or plus. In which case you actually get additional constraints, you get much more information, and you also get dynamics because you can see radial velocity information. So you can measure winds on planets. You can measure the orbital speed of the planet in real time, etc. So those are the regime. If you have a perfect detector, you should always go to higher spectral resolution. In terms of the wavefront sensing, there is a lot of value in having wavelength information when doing wavefront sensing, but that's probably up to a resolution of maybe 20. After that, there's not a lot of gain. And because wavefront sensing needs to happen at kilohertz speed, we don't have a lot of photon anyway per frame. So there's not enough light to essentially think about much higher resolution. So I hope that answered your question.
Yeah, thank you.
Any other questions from this room?
What do you think is the largest uncertainty in getting to the end goal of imaging and taking a spectrum of a habitable planet with the ELTs? Is it something in what we understand on planets and the spectrum of the planet, or is it something in the atmosphere of the Earth, or is it a technological problem?
So the question is, what are the largest uncertainty in essentially the path to obtaining spectra of habitable planet atmospheres? There are many. I think one of the big uncertainty on the science side is, do planets in the habitable zone of M-type stars even have an atmosphere? They are likely tidally locked. The low mass stars tend to be very active when they're young. There are concerns that the atmosphere may be that will be looking at essentially dead rocks. But there's no good data on it. It's models. There's no agreement on this, so we should be looking. So I think that on the science side, that's the main uncertainties. Are habitable zone rocky planets around M-type stars actually suitable for life itself? And we really don't know. On the technical side, there are many uncertainties. The high contrast imaging work at sort of 10 lambda over d separation is much more mature than trying to push contrast at very small angular separation. So a lot of the challenges of getting high contrast, when I talk about high contrast, is a raw contrast of 10 to the 5, let's say, at 1 to 2 lambda over d. That's quite new, and that hasn't really been pushed very much. The fundamentals of it tell us that it should be possible, but we know how much gap there is between fundamentals and reality. The things that some of the uncertainties are linked with, I mentioned predictive control. We think predictive control is actually quite important to achieve this goal because these stars are not super bright. We're going to have to be quite optimal. And so the predictiveness of the atmosphere is one of the question mark. And it's just, I think a lot of things when we look at the individual error terms or very sort of focused on one of the aspects, we can get a warm feeling, but there's a lot of work to bring that to the system level, a huge amount of work. And then we see that already in the development we're doing. It takes a lot of, there's a lot of surprises along the way from getting something to work on paper, even with a good model of the hardware, to getting it to work as part of a system.
Any other questions, Suzanne?
Going back to the methods that you were talking about, this algorithm, this learning algorithm to correct for the focal plane. Is that real-time like machine learning algorithm, or is it post-processing?
So the one that I showed was actually a real-time. I'm bringing up the slide and I'll explain. So the question is, what is this algorithm that learns from the focal plane that I mentioned? I think you're referring to this slide, right?
Yes, because my understanding of using a machine learning algorithm, the largest problem is that it's often too slow for real-time correction.
Yes. Yeah. Yes. So the comment was maybe a machine learning algorithms are too slow for real-time correction also. So this is a big area of development right now. We've a growing number of people actually gaining interest in this. This particular slide that I showed is the simplest form of learning you can do, and it's essentially a binary classifier. It's looking at the image in the focal plane and deciding is it good or is it bad, and reinforcing the wavefront control loop every time there's a good image to tell it what you saw in your wavefront sensor at that exact time was good. Please keep doing that. So it's essentially updating the reference, the convergence point of the wavefront sensor. So it's a very simple but powerful idea. It's basically we watch the image at high speed. Every time we get a better image than the average of the previous one, say, hey, we should go that way. And we gradually update the adaptive optics system to keep nudging it in the good direction. So that's the simplest form. It's a binary classifier, good, bad. There are much more advanced things that algorithms use, relying on machine learning approaches, especially for predictive control, that are in development. They're at various stages of maturity, haven't been running in real time on Sky yet, but we've been looking at this and it looks quite promising. There are, and we've started to benchmark some of this machine learning inference tools that are developed for real-time deployment, and they seem to be able to run at kilohertz speed. The training is slow usually, but once you have trained, the inference is fast.
Thank you.
Questions from Zoom? Just maybe go ahead and speak up. We can't see anything.
Let me unmute.
We can hear you, Esther.
Okay, so actually, this is terrific talk. You had some terrific slides up, and I have a whole bunch of questions, but I'll focus on one thing, which is it struck me how many of these complementary things that you were talking about actually apply to things that you can optimize with Subaru, not just where you were talking about for the trade-offs in terms of the detectability and the spectral types of stars, but also because all these other things that you were talking about, like the high contrast, the darkness of the sky, being able to do direct measurements of the speckles monitoring, you know, in your plot, when I looked at the response curve, and I looked at about 1 micron and 1.2 microns and the features, and I knew how dark the sky was there, and I knew how much, you would gain both in the predictive technology and the responsivity of the Subaru Telescope at those wavelengths. I was thinking, wow, you have a really, really winning combination, not just for the science goals there, but all those things that you were talking about direct monitoring the telescope where it was dark, about, advancing things. Can you talk a little bit about how well that figures in both the science goals and the things that you can do, like with SkexAO, specifically on Subaru, because you really, really have nailed it for things like that.
Yeah, thanks for this comment/question. As you picked up, I think we're at a very ideal time to push these technologies forward, and there's a convergence of multiple enabling factors. Access with flexible access to a large telescope is key, and Subaru has provided us. We've been very fortunate to have this at Subaru with a large. I showed a large NASMIS platform, and a lot of collaborations. This is a work that requires a lot of people, and so we've been engaged in many collaborations with groups that bring technologies. I sort of joke that my job at Subaru is to reduce the cost of failure, because inevitably when we test a new technology, it doesn't really work at the beginning, and so a lot of it so that's why it's hard to do on a large telescope. You show up with something that doesn't work. And the large telescope is not going to give you several nights of time to figure it out. But if you don't have the access to the large telescope, it's difficult to get the resources to make it work in the lab or on a small telescope where you're going to face other problems because the telescope is small and it doesn't have a huge team to support it. So there's a mix of enabling technologies, but also the infrastructure to be able to bring those technologies up to speed. In terms of technology, detectors, advances in detectors have been key. Advances in computers have been key. Optics, manufacturing. I talked about photonics devices. 20 years ago, this was a dream. Now it's real. We can put it on sky. So it's really a convergence of all those things coming together that enables us to advance. I'm not sure I answered your question, which is quite broad, but I added a few comments to it.
Okay. Well, I think what I was saying is that I am really, really impressed that many of the things that you were telling us about in the pieces actually would work so well for testing at Subaru. It's partly like the responsivity at the 1 micron and 1.2 micron edge. It's partly the darkness of the sky, but it's also the red CCDs there. It's the fact that if you're doing things with speckles and direct detection and contrast, and in that wavelength regime, you really, really are set up to do this both at the high contrast and the darkness of the sky, and I'm thinking even in the detectors that are being used, even if I were doing this and just doing this in the optical, there are just so many things that appear to be multiply testable at the same time of things that are coming on, that I think even without just doing and saying we succeeded, you're in a really, really, really good place. I think about where the key lines are, where I want to be in the science, and I'm sort of cross-calibrating all the things that showed up in your different slides, okay? But I'm also really, really impressed at things that I didn't expect, like, and that's not that's not specific to those regions. I'm really, really impressed with how much you've been able to do with polarization images, right? I really didn't know that it was that advanced as far as the detectors. And I also had simple questions that I'm afraid to take time asking, because it has to do with your direct sampling in those images, when you casually said in your HR slide, this is okay, and these are the places where we're actually sampling things, you know. You know, I'm going, wait, how's he doing that? How's he doing this at the same time? You know, and so it was a really impressive presentation, not just by what you said, but how you put the slides together and how people could make deductions and ask questions about the things that were coming. That's my comment.
Oh, thank you. Yeah, and if you want to discuss some of those things offline, I'm happy to go deeper, you know, in some of those details. Yeah.
I'd be great.
Olivier
It'd
still
be great.
has
I'll
some
do it
slots
offline.
available. Yeah, there's still some slots available for meetings. Olivier has kindly made some time available tomorrow as well. We have time for one quick question remotely, if anyone has any left.
Yeah, I've got a question. Just a quick one. Would a laser guide star help? Supposing you could put some laser guide stars 10 or 20 or 30 meters upstream, it would help you understand what's going to come flowing through your beam momentarily.
That's a very good question, because we're wondering exactly that. So it used to be that we thought laser guide stars would not be helpful because as a primary beam, they're kind of much dirtier than starlight. They're extended. They come with a slew of challenges. However, the science is driving us to try to image planets around stars that are not super bright. M-type stars are not very bright, and so we're curious about this question that you asked, and especially you picked up on something quite interesting, is that if you have laser guide stars that are off axis, you can experience turbulence before it is pushed by the wind into your beam. So we hope that it can be extremely useful in terms of predictive control. One thing I didn't have time to mention is there is a project at Subaru Telescope to do laser tomographic adaptive optics. So within about a year, that we will have 5 lasers, 4 of them off axis, 1 on axis. We'll have 4 wavefront sensors, and we definitely want to play with that, see if that can be helpful. That's an open question, a very good question, and yeah, we don't know the answer, but that it may actually be quite useful.
Okay, let's thank Olivier again.